So let's look at question 12. It says a horizontal disk that has a hole through its center. A string passes through the hole and it connects to a mass M on the top of the disk. To a bigger mass, big M, that hangs below the disk. Initially, the smaller mass is rotating in a circle at radius r. What must the speed of M be such that the big mass stands still? So this obviously is a question where there's no numbers, but we can understand and work through the problem without that. So let's label this, right? So here's r, that's little r there. And then obviously we have big mass or little mass here and big mass there. So if we look at the individual masses, right? So let's look at little mass here, and it's rotating, right, in a circular motion. And there's just really one force that's really acting in that circular motion. So this obviously has a normal force and it has a force of gravity, but it also then has a tension force here. And it's the tension force which is going to be causing it to go in a circle, right? Normal and gravity aren't really acting in this case, right? So if we were to draw it over here, this is normal and that's gravity. Those don't play a factor. It's just this tension force towards the center of my circle. Okay, so I'm just going to erase gravity and normal because they really aren't going to play a factor in this question. Okay, and then for the big mass, which is down here, big M, we have two forces here as well. We have the force of gravity and we have our tension. And I like that it says we make sure that the big mass stands still. So that basically tells me that the F net on the big mass has to equal 0. So if that's true, then the sum of the forces on the big mass must be the tension minus the force of gravity, which is 0. And so that's going to tell me that my tension equals my force of gravity, which is mass times little g. So, and what we're also going to know is that the tension in the little mass is going to equal the tension in the big mass, right? Because it's one string, so the tension itself everywhere is going to be exactly the same. So that gives us our force of gravity, or excuse me, our centripetal force, right? Because it's the tension force that's causing the centripetal motion. This gives us what that value is going to be. And actually I'm going to change this to big M. So we can designate the two. And so let's then find, it wants us to find, right? Find the speed of little m, right? So we're going to use the equation force centripetal equals the tension, which is equal to the mass times velocity squared over r. Our tension force is going to equal big M times g. We're getting that from here. Equals little m v squared over r. And now we just need to do some algebra to solve for v. So I'm going to multiply each side by r. Get rid of my r's. So I get big M, little g, r equals m v squared. And I'm going to divide by little m. Little m's cancel out. So I'm left with velocity equals big M g r over little m square root. So that's going to be how fast I need to be going, dependent upon the masses as well as the radius of its motion. So I really like this question. It does a really nice job of just setting it up and also just understanding how we can work through these types of problems again without any numbers. Because again, that's the process. The numbers don't really matter. If we can work through a problem and get to what our final velocity needs to be or whatever we're looking for, then we can do it regardless of the numbers.